To determine how good our model is, we can estimate the coefficient of determination. We're already familiar with it, and we know that this is a measure that represents the proportion of the total sample variation in Y that can be explained by the estimated model. The formula is the same, but this is out of the scope of our course. We will not focus on it, but what we need to remember is that it always lies between 0 and 1, and unfortunately it has one limitation. So the coefficient of determination is a non-decreasing function of the independent variables. So the more variables you add, the higher this coefficient is. And the problem is that you can add a lot of variables and most of them can be completely meaningless, but the R-squared will still show that the fit of the model is very good, that the model is very good at explaining your dependent variable. But luckily, econometricians and statisticians have come up with the way to deal with this problem, and they've developed the so-called adjusted coefficient of determination, which is dependent on the value of the original coefficient of determination. But in comparison to R-squared, to the traditional R-squared, the adjusted coefficient of determination takes into account, let's say, adjusts for both the sample size and the number of parameters. And therefore, this coefficient cannot be forced to 1 simply by adding more and more independent variables to the model. So actually, this coefficient sort of punishes you for adding more variables, and it appreciates when you increase the sample size. Therefore, the adjusted coefficient of determination will always be smaller than the traditional coefficient of determination. And another measure that allows us to say whether we have a good model or a bad model, so to make a conclusion about the model's utility, is the F-test for the overall usefulness of the model. And the test is conducted in the following way. So the null hypothesis is that all the estimated coefficients, all the estimated slopes, beta 1, beta 2, all the way to beta k are simultaneously equal to 0. And the alternative hypothesis is that at least one estimated slope is not equal to 0. To do this test, the following test statistic is estimated. F is equal to r squared divided by k, and everything divided by 1 minus r squared, which in its turn is divided by n minus k plus 1, where we know is n is the sample size and k is the number of slopes in the model. So this is a new type of statistic. We haven't seen it before. We've only worked with t-statistic and z-score. So let's say this is the fourth, because we also had chi-squared. So this is the fourth statistic, and it follows the F distribution. You can easily get the table of the F distribution on the internet. And the decision rule is similar to all the other decisions rule we've seen so far. So the null hypothesis that all the coefficients are simultaneously equal to 0 is rejected when the estimated F value is higher than the critical F value at the level of significance alpha. So we will reject the null hypothesis and accept the alternative that at least one beta is not equal to 0 when the estimated F value, so this test statistic, is higher than the critical value that we will get from the table.